We live in the age where everyone wants faster and reliable internet by paying more money to internet service providers. But the secret here is we can actually get better internet by configuring our home router. The key issue here is traffic buffer boards that causes a disappointment in internet performance, especially when it comes to video streaming, online gaming, or voice over IP. Buffer boards is delay that happens when there is too much traffic in your network, more than the capacity of your router. It's like a traffic congestion on a highway. Some studies show that majority of home routers are using a conventional queue management to resolve this issue. However, it has some limitations that can decrease the internet performance. That's why we need a better solution, which is active queue management in this project.
The solution for buffer board is active queue management. AQM drops packets based on queue size or time spent in queue to avoid congestion. Here we have taken two AQM protocols, Pi and FQCuddle. As shown in the figure, Pi drops a packet from head based on the depth of queue, which means it monitors the depth and adjusts drop probability to provide space for incoming packets. Another solution for buffer board is FQCuddle. FQCuddle creates different queues for incoming packets based on hashing algorithm, as we can see in the picture. Scheduler sends packets one at a time from each queue by using round-robin method, as connection will get fair distribution of available bandwidth. When queue is full, FQCuddle drops a packet which has been in queue for a longer duration. So FQCuddle is multiple queue management algorithm. Packet drop rate is low as compared to Pi, which is a single queue management algorithm.
The main purpose of this project is to examine the effectiveness of conventional queue management FIFO and AQM's FQCuddle and Pi in a variety of realistic scenarios that imitate home network connections. In addition, we design a set of comprehensive technical documents for configuring AQM in a Linux-based home router. We believe that together, these factors can provide the optimal approach to configure AQMs for home users who can configure their routers based on experimental results presented by this project, thus experiencing an efficient network performance.
We aim to do the testing first on the virtual testbed to become familiar with the Linux operating system and open the PLT router. When we are confident with the virtual testbed, we move on to the physical testbed. The test run in a controlled environment that consists of 3 computers, a switch, and a router. At first, our goal is to test different traffic types in a variety of home connection settings. However, it will be significantly time-consuming, thus the client agreed to rescope the project. Henceforward, we tested only one traffic type with different network settings and collect the result. When all the results are collected, we then construct the graph to evaluate the result. We can clearly see the throughput changing with different network settings.
There was a significant amount of delay in the project as we met with our client in week 6. Furthermore, none of us had strong knowledge of Linux and Bash scripting. In addition to that, due to restricted budget, the team members had to utilize personal laptops to conduct the experiment. Having experimentally evaluated the performance of different queuing techniques and a range of typical home network traffic, we found that AQM techniques help to reduce delays in flows. FQCuddle showed optimal network performance since it provides fair sharing of bandwidth capacity for each flow. Therefore, with the use of AQMs and FQCuddle in particular, home users can experience high performance in their TCP-based applications. Further work can involve investigation of different real-time traffic types such as video streaming and VoIP calls. We highly recommend to utilize the automation testbed to save time for experimental setup and data collection.